part 2 of this. This is the second half of 7.1. We're going to talk about hypotheses tests and p-values along with steps to do a hypothesis test and some example problems. Okay, first things first, this chart. So, we did a couple of them where we talked about the population or anything, and it was a proportion, so we called it P. Mean, we call mu, and we will not be talking about variance. But P meant proportions for the population. Mean was the population parameter for mean. Remember, it's just the Greek letter mu. If it's a test, if it's a sample test statistic, it'll be p hat and x bar. Remember, x bar is just another way to say mean as well. But this is for a sample test statistic. These standardized test statistics, these are critical values. We've talked about them. Critical values, the z-scores, z sub c. So with proportions, it's that same exact z-score we've been talking about. With means, though, it's gonna be z so long as we're talking about a sample of over 30 people. But if it's a sample of less than 30 people, then it's a t-score. And we'll get into that a little bit more in a different section. Okay. Alright. If your alternative hypothesis is less than the null hypothesis, remember your alternative is HA and your null is HO. Your null hypothesis is just your statistical hypothesis that includes equality. So anything with an equal sign, equals, less than or equal to, greater than or equal to, as long as it has some kind of equal, is a null hypothesis. If it does not, and if it's not equal to, less than, or just greater than without that equal sign underneath the inequalities, then it is an alternative hypothesis. So if our alternative, we're looking at less than. So HA we're going to say that our mean is less than the null hypothesis, which we're going to just do it like that. And if we have less than in the alternative than in the null hypothesis, you got to flip the inequality and throw an equal sign underneath it. Alternatives do not have that equal sign underneath the inequalities, and their equals is not equal to. Null hypotheses do have it. So the way this would look when you graph it is, again, labeling these -3, -2, -1, 0, 1, 2, 3. Since we're working with z-scores, remember z-scores have a mean of 0 and a standard deviation of 1. So the mean goes in the middle. To mark the next one, you add by 1 on the right, and you subtract by 1 on the left. Alright. This means that our z-score is going to be about in here. And since we are less than the null hypothesis, we're going to shade the left side. And this orange is going to be our critical region, because this is everywhere where the alternative is less than the null. And if I gave you this picture, just this picture, with this left side shaded, you should be able to tell what kind of a tailed test this would be. Because look, which side is shaded? It's the left side. So if the left side is shaded, then it's just a left-tailed test. And we want this bottom part. We just want the less than, because that's what our graph looks like. we're saying that the region that's shaded is less than this. Now, if the alternative is greater than the null hypothesis, then we would write that mu is greater than k. So then to do the null hypothesis, flip the inequality and throw an equal sign underneath it. Alright, again, labeling this -3, -2, -1, 0, 1, 2, 3. Since we're greater than, we're going to be on the right side. And we're going to shade the right side because we're going to shade the side that's greater than this line. And again, this is our critical region. And if I just gave you the shaded picture, you should be able to say that since the right side, this right corner is shaded, this is a right-tailed test. And we want this bottom one because these two match. You're saying that you shaded the region greater than this number, which over here we have it written as Z, but over here I have it written as K. It's the same number. It should be the same number. But in this case, it could be just a regular number, and then you change it to a z-score to fit this graph. Or you could have graphed it using the mean, the original mean and the original standard deviation. But if it doesn't give you that, we're just gonna go this way. But if your alternative is not equal to the null hypothesis, should be an HA here and an HA here. That means that we are not equal to K. If you're not equal to, the complement or the opposite of that would be to be equal to it. Okay, again, just label -3, -2, -1, 0, 1, 2, 3. Now when we're not equal to, that means we have two different regions. We have two sides. So now we have two critical regions. The other ones we had one on each side, but this one we have two. So if you remember, if you have two critical regions, that is a two-tailed test. Because you have two critical regions. So what this is, all I've done so far is, before when we defined left-tailed, right-tailed, and two-tailed, I just drew a picture and I did the inequality. But this is how it would look like. This is the what the graph of a two-tailed test would look like, and this is how you would write it in null hypothesis, in the alternative hypothesis, and in the null hypothesis. The right-tailed and the left-tailed are the ones that we did earlier. But now you can see it in picture graph, what it means, and in written graph, and be able to tell whether you see this one or you see this one. It is a two-tailed test. Whether you see this picture or you see greater than, it is a right-tailed. Whether you see this picture that's shaded on the left and less than, it is a left-tailed. Alright. Then, a small p-value is considered an unusual event. This gives us more evidence to reject the null hypothesis. So when you're trying to figure out if you need to reject the null hypothesis or not, the p-value normally comes in handy. If it's small, it's considered unusual and you're more likely to reject it than you are to accept it. So we need to define what a p-value is. This is just probability the null is true. So if your p-values are small, your probabilities that the null hypothesis is true, people like to go with the greater probability. So if we have like a small p-value, where p-value is the probability the null is true, then the probability that the null is not true is a higher probability, and they're going to go with that. That's why people would reject the null hypothesis more often if you have a small p-value than if you had a large p-value. Alright, so to perform a hypothesis test, you first, like we did in the last part, you have to state your null hypothesis. And your alternative hypothesis. So this is where you say H-O-H-A. You state the null and then you state the alternative. Then you need to identify the significance level. Which we're going to actually talk and say that it's going to be this Greek letter alpha. It's actually a lowercase alpha. Alpha equals. That's your identifying the significance level. Once you have that, then you will be sketching the standardized distribution. Standardized. Y'all know I'm not the best at spelling. So remember, that's just 0 in the front, and then 1, add 1, 2, add 1, 3, subtract 1, subtract 1, subtract 1. That's a negative 3 right here. This is your standardized distribution. Alright, so sketching it would just be, if this graph isn't drawn, draw it and label it from -3 to 3. Once you have it sketched, then you need to mark the critical value on the graph and shade. So you'd mark it wherever your z-score is, and then you're going to shade. When you shade, you need to look at your alternative hypothesis. Your HA, your alternative hypothesis, is the one that's going to tell you how to shade. That's why I had this marked, is your alternative hypothesis tells you how to shade. Not your null, your alternative. HA. Salem's going crazy in here. Okay, then using our calculator, we will calculate the p-value. If you can hear all that noise, then that is my cat having his crack hour. So he's gonna make a mess and go crazy for a little bit, but it's fine. Alright. We'll get into this more often. We'll get into calculating our p-value in a different section, but these are our steps. This one is just an introduction, so we're really going to be focusing more on that claim, the hypotheses, the null and the alternative, which way our tail direction is going to go, and our potential errors. Oh my gosh, Salem. I don't know what's wrong with that cat. He's like going crazy right now. It's on a TV stand. He goes on the top of the fridge, knocks everything down. Alright. Oh, we only got 5 and we're still at 7. Oh yeah. Okay. So 6 is compare your p-value to your significance level alpha. So when you're comparing them, your question to ask is p less than or equal to alpha? So put your p down on the left side, less than or equal to, and then put whatever your significance level is, which we have already we will have already decided what it is, because we're gonna that's step 2, is identify that significance level. Now this can go 2 ways. This is a yes or no. If your answer is yes, if your p is smaller than your significance level, then you need to reject your null hypothesis. The probability that that null hypothesis was true was too small to take a risk on it, so we're just going to reject it. If your answer is no, if your p-value is greater than, as if we had 6 less than or equal to 4, that's not true because 6 is greater than 4. Then you just failed to reject it. So what that failed to reject means is that you didn't reject it, you accepted it. That's all that means, is you didn't reject it. Then once you have that, then you gotta be like, okay, well, you either rejected your null hypothesis or you accepted your null hypothesis. Either way, now you have to figure out and interpret this decision to your problem. Because remember, when we're working with null hypothesis, our first thing is when you start with a sentence that has all the meaning, then you just go to claim, so then you just go to math. P equals something, mu equals something, then you go to your hypotheses, then everything that we do is not going to be in numbers and letters and words. Well, it's not going to be in words anymore, it's all in numbers and letters. So once you have it, you're going to be like, well, I accepted that my null hypothesis is P equals something. Then you got to be like, okay, well, that P equals something, back to your problem, what did it actually mean? What did we start off with? Because nobody likes looking at the math. Like I've said before, nobody really likes looking at the hard math part of how you got your question and your answer. They just want to know the process of it. They want to know what you concluded. And as long as everything went right, they're good. They don't want to know those tiny little details that you went through. You might just talk a little bit about them, but skim over them if you were doing a presentation over all this. Alright, so in this bottom part, we're going to state our hypotheses and identify the claim. So we're going to determine if the test is left-tailed, right-tailed, or two-tailed, and then you're going to state your potential type 1 and type 2 errors. So this first example is texting while driving. The proportion of high school students who text while driving is 78%. I'm actually going to use green. Alright, remember, if you see the word proportion, that's P. 78%, that means the decimal is right up behind it, and you move it to the left twice to make it into the decimal of 0.78. Or you take or you could take 78 and divide it by 100, and you would still get 0.78. Is means equals. So just by doing this, I've already written out my claim. So my claim in this sentence is that P equals 0.78. Now once you have that claim, now you need to state your null hypothesis and your alternative hypothesis. So using your claim, once you have your claim written down, this part is easier because you have to say, okay, is there equality in my claim? If your answer is yes, then you put this in your null hypothesis. In this case, we have a yes, so we're going to put this in the null. And then to do your alternative hypothesis, it's still that same p.78. The only thing is the opposite of being equal to something is not being equal to that thing. So now we've stated at both of these. Now to figure out what your tail direction is, remember that you need to look at your alternative hypothesis. When you look at your alternative, you'll notice that we are at a not equal to. And if you go back to your 3 graphs that we drew at the beginning, you can see that if your alternative hypothesis has not equal to, you are a two-tailed test. So that would be your tail direction, two-tailed. And when it says explain, you can just put that because HA is not equal to. That's the only reason. That's what tells you is this sign right here in your alternative hypothesis. The sign that you have, the inequality that you have, is what tells you what kind of tail direction you have. Then your potential errors. Your type 1 error and your type 2 error. In this case, remember your type 1 error. I should rewrite this just in case. Okay. Type 1 error just means HO is true, but you reject it. Type 2 means HO is not true, but you fail to reject it. You fail to reject it. This is its own little box. Remember, just failing to reject it means you didn't reject it, so you took it. So in this case, our type 1 error would be, if HO is true, that means the proportion of students texting while driving is 78%, because that would mean HO is true. But we have to reject this. So, but we conclude it is not. So that's what we did. We said that our null hypothesis, which is that the proportion is equal to 0.78, proportion is 78%, is true, but we conclude that it is not, and when you conclude that that is not true, then you just rejected your null hypothesis. And then our type 2 error would be that our null hypothesis is not true, but you fail to reject it. So that would just say that the proportion of students texting while driving is not 78%, but we think it is. So we just stated that our null hypothesis was not true, but we didn't reject it, so we said even though it's not true, but we think it is, so we're going to conclude that it is true. We did not reject the incorrect null hypothesis. It's a little confusing at first, but after a little bit, you kind of get the hang of it. Okay, last two examples. I don't know if I'll go over both of them. No, I think I'm just go over this first one. The second one is completely filled out on the notes page that would be attached to the link to this video. And I'll have y'all's homework assignments out probably, hopefully, by the end of today. I'm working on them. Something nice and simple. Sorry, this quarantine got me bored. Alright, so the mean life of iPhone batteries is less than 2 years. Mean is mu. We have a 2. Less than just means the arrow points to the left. Greater than means the arrow points to the right, because if you look at a number line, these are all negative numbers, these are all positive numbers. So if your arrow points to the left, then you're pointing in the negative direction, and all of these numbers are less than. You keep getting smaller. But if your arrow points to the right, then you're greater than, because you keep pointing to all the bigger numbers. I know some of y'all still have a little bit of trouble figuring out which one is which. Okay. Alright. So I'm gonna write my claim down. I'm going to write my null hypothesis and my alternative. There we go. Alright, well, we already have our claim right here. Your mean is less than 2. Okay, so when you're trying to, since there is absolutely no equality in this claim, there is no equal to underneath it, then that is your alternative hypothesis. So then to find out your null hypothesis, you would write down your mu, write down your 2, flip the inequality, and throw an equal to underneath it. And bam, it's done. Alright, so looking at this, tail direction. Remember, your tail direction goes back to your null hypothesis. Looking at this null, we have mu is less than a number. So looking back here, mu is less than a number. It matches, so you're automatically left-tailed. Or notice that the arrow is pointing to the left. If you didn't notice this, in your HA, your arrow is pointing to the left, so you're left-tailed. Had your arrow been pointing to the right, you'd be right-tailed, but it's not. The direction this arrow is pointing tells you what kind of test. Why? Because we had a less than sign in there. So your potential errors, I had to write small. Okay. In our type 1, that means our null hypothesis is true, but we reject it. So our null hypothesis is mean stands for phone batteries, the life of a phone battery. So we're going to say that your first step on determining the type 1 is to state your null hypothesis is true. So battery life is greater than or equal to 2 years. So we just stated that that's true. So our battery life is greater than or equal to 2 years. State the null hypothesis. Throw in your but. But we think it's less. So you started with your null hypothesis stating that it's true. So we stated our battery life is greater than or equal to 2 years. That's our null hypothesis. That's true. But we have to reject it, and to reject it, you're going to say the opposite. But you think it's less than 2 years? There you go. So to do the type 2, you'd start by stating that the null hypothesis is not true. So in this case, since we are greater than or equal to, we're going to say that our battery life is less than 2 years. That's the only way that this would not be true, is if it was less than 2. But now you're going to conclude that it's actually the null. So, our type 2, we stated that our null hypothesis was not true, which would be to say that we were less than 2. Hey, Salem, down! But then we're going to conclude that it is true. I'm sorry, Salem keeps trying to eat the birds that my mom has. Alright, that is the end of that. The second example is just like this one, except with decimals and money and stuff. It is highlighted and done in the completed notes that I will be posting along with the link to this video. If y'all have any questions, please let me know in time for me to answer them. You'll have 2 assignments again to be done by the end of this week. Don't put them off, guys.